To talk about polynomials, we need to understand the language that we use. First of all, the definition of a polynomial is that it is the sum of terms of the form a times x to the n. In this definition, a, which we call the coefficient of the term, can be any real number, whereas n, the power of the term, we call the degree, and it must be a whole number. A whole number is a number that is not negative and doesn't have a fraction part. For example, 0, 1, 2, 3, etc. No upper limit on how big it can be. So looking at this example in front of us, we can see that we have 5 terms in this polynomial, and just looking at the first term, it has a degree of 18. And this term has a coefficient of 5. It's also conventional to write these in order of descending powers. That means that as you read from left to right, the powers get smaller. We start with the power 18, then we go down to 12, down to 7, down to 3, and finally this last term is really a degree 0 term. This is 4 times x to the 0. That's how we make it fit the definition of a polynomial, and that's also how we determine the degree of that term. So for each of these functions in the table, we're going to answer whether it's a polynomial, and if so, we're going to find its degree and leading coefficient. So once the polynomial is written in this order of descending powers, that first term is the one that speaks for the whole polynomial. Five x to the 18 is a term of the polynomial. It's also the leading term, and its coefficient is the leading coefficient of the whole polynomial, and its degree is the degree of the polynomial. So, looking at this first example, f of x equals the square root of x plus 2. This is not a polynomial because of the square root. The square root is not a term of the form a times x to the n, where n is a whole number power of x. It doesn't allow for anything other than whole number powers. This second example, it looks a little bit more unusual, but this is a polynomial. And the way that we can see it fitting the pattern is to write it as negative 0.6 x squared, that's our highest order term, plus pi times x to the 0. So remember that even though the powers have to be whole numbers, the coefficients can be any real number, and pi is a real number. So this is a degree 2 polynomial because 2 is the largest power, and the leading coefficient is the coefficient of the leading term, or the term with the highest power, so the leading coefficient is negative 0.6. Looking at the next example, m of x, both of these could be written as powers of x, but if we were to write it in another form, it would look like this: 2x squared minus x to the power negative 1. Negative powers are what cause us to take the reciprocal, therefore ending up with x in the denominator. So this one we would answer no. Even though it can be written as powers of x, they are not whole number powers. Finally, our last one we would want to think of as being x to the power 0. There is no minimum number of terms to satisfy the definition of a polynomial. Even though poly means many, we don't have to have more than one term to satisfy the definition. So this one we would say yes, even though it is a degree 0 polynomial, and its leading coefficient then is 3. The process by which we graph piecewise defined polynomials is very similar to the process by which we graphed piecewise linear functions. However, we do need to be very cautious with our graphs in order to make sure we can tell whether or not the pieces match up. So we will first take a look at y equals 7 minus x squared, which I'm going to rewrite as y equals minus x squared plus 7. This makes it a little bit easier to see what the transformations are. The minus in front of x squared is a reflection about the x-axis, which makes the parabola open down. The plus 7 is a transformation that is a shift, a vertical shift, up 7 units. So we're going to draw the graph of y equals x squared, shifted up 7 units and opening down. That puts the vertex right here at 0, 7, and the graph of y equals x squared passes through the point 1, 1, the point 2, 4, and the point 3, 3, 9. So I'm plotting these points relative to the vertex but going down instead of up. Then reflecting them about the line of symmetry and drawing the parabola that passes through them. I now see that I want to restrict this to the interval from -4 to 2, so I'm going to find both of these values on the x-axis. -4, +2, and anything that is outside of those intervals I do not want to include, so I'm going to come through and try to erase those parts. You'll be able to see some remnants of my graph here because I don't want to erase the whole grid, but it should still be clear what parts I'm keeping in my final graph. I have to extend this just a little bit further to see where we get to at x equals -4. That's going to be 16 units down from here, so it's going to be all the way down here at 9. So let's bring that graph down just a bit more, and I'll come back and erase these arrowheads, which I don't really want. All right, so that's the portion of the parabola that I'm going to keep. Now I'm going to focus on the second part of the graph. The second part is y equals 3, which is a horizontal line. This is going to be pretty easy to graph, and the horizontal lines we can draw and pretty much think about the x values at the same time because there's not a whole lot involved in drawing a horizontal line. So I'm going to identify 8 over here. I've already identified 2 on the x-axis. And I will draw the graph of y equals 3 as a horizontal line connecting those points. Now I can see, because I graphed this carefully, that they do in fact, the graphs do in fact meet up here at this point. So I don't have any jumps in the graph. I'm going to go over in black the part that I want to keep just to make sure that it's really, really clear. So this is the graph I end up with. Again, same process as graphing a piecewise linear function in that we want to consider each of the individual pieces, do whatever we need to do to get that graph established, then think about restricting it to the x values that we want to keep for that particular piece of the graph. At the end, we can go through and figure out whether the points or whether the individual pieces meet up or whether we have jumps in the graph for which we have to determine open and closed circles, following the same process we follow for piecewise linear.